Hello and welcome everyone to the seminar. My name is Farid Pasha and I'm a Wolfram certified trainer here in Wolfram Research. This presentation is about solving numerical computations in Wolfram language with the focus on one of its unique strengths, which is the ability to use symbolic computations in numerical methods. I will begin with a quick review of the main numerical functions available in Wolfram language and will include examples of the ways how you can use them. Then before I get into detailed examples, I am going to take a couple of minutes and give a big picture of why symbolic computation is so valuable in numeric analysis. And I will also compare how traditional methods are compared with Wolfram language. After that, I will talk about the first big advantage of having symbolics for numerical computation, which is the ability to infer from users' inputs which algorithms are suitable for solving that specific problem rather than user guessing which method to use. I will proceed by giving a couple of examples of numerical methods in Wolfram language that fundamentally rely on symbolic computation and hence impractical, or I will say rather impossible, in any traditional numeric computation only system. Once we have established that with examples, I will talk about benefits of performance that symbolic can bring. These includes many automatic optimization that Wolfram language applies. I will demonstrate how to control algorithms and finally how to monitor them while they are running. So let's begin with a brief overview of the very core and some of the major numeric functions that are used in Wolfram language and their applications. The Mathematica function that performs numerical integration or quadrature is called NIntegrate. The Wolfram language function NIntegrate is a general numerical integrator. It can handle a wide range of one-dimensional as well as multi-dimensional integrals. Here we apply it to a function of one variable, and then we can also see the plot for that. If you want to integrate a list of points rather than a function, then first you need to interpolate your points, and then you can use NIntegrate as usual. To compute a path or contour integral, first parameterize the path. Here we parameterize the contour that circles the point z is equal to 2 in the complex plane. F of z is the function we want to integrate. We can then perform the numerical integration by using the chain rule here. And we can get the answer. This integral you see here corresponds to the complex residue calculation. So we can check out the result using the built-in residual function. Here is a simple example of solving an initial value problem. This solution in this case is available here. Similarly, NDSolve solves ordinary and partial differential equations. Here is an example of solving a second-order nonlinear differential equation. Here is another example of solving an initial value problem. And we see the solution in this case is a sinusoid. NDSolve also handles delay and differential algebraic equations. So here is an example of solving a delay differential equation and then seeing the plot for that. Here is a much more exciting example of solving Schrödinger equation. The solution gives the probability of finding a particle at a given position and time. In this case, it's a particle rolling back and forth in a periodic well. A useful special function of NDSolve is to get a numerical indefinite integral. In this case, we want to integrate an approximate function. This is equivalent to f satisfying this equation, which we can solve with NDSolve. We then have the indefinite integral function as an interpolating function, and then we can also animate the function along with its integrand. The core function of solving numerical equation solving is findRoot, which searches for a numerical solution of one or more equations. Here is a very simple example that can't be solved in closed form. One important application of findRoot is setting up numerical inverse functions. Given the definition of y of x, how can we find x of y? We can define a new function, inverse of t, where each value of t numerically solves the equation of y of x is equal to t. Resulting function can be used as any other function in Wolfram language. Each point on this plot involves one call for findRoot. Wolfram language has numerical functions for both local and global optimizations with constraints. Function findMinimum searches for a nearby local minimum, whereas function nMinimize works much harder and finds the global minimum. Both findMinimum and nMinimize can also perform constraint optimization. In this example, we constrained x and y to points that satisfy this predicate, and we find the global minimum at the boundary of the region, which we can also see in the plot. All the 3D plots in Wolfram language, you can rotate them, zoom in, zoom out, and play with them. There are many linear algebra functions available in Wolfram language. NIntegrate is probably the most important one. Here is a simple example of solving 4 linear equations. And here is a larger example of solving 20 linear equations with random real value coefficients. An important concept related to linear algebra is sparse arrays. Wolfram language has special sparse array technology for efficiently handling arrays with literally astronomical number of elements. The function sparse array creates a sparse array of any rank from a list of rules or a dense array. You just specify the location in the matrices where non-zero elements are. And here you can see in this example, there are 10 non-zero elements in this 8 by 8 array. And here is a matrix plot of the resulting array. Here we construct the system of linear equations corresponding to this discretized model. You can see that it is a 900 by 900 system, but only around 4,300 of the elements are non-zero. And here is a matrix plot of the overall system of the equations. With this, I conclude the quick and brief overview of some of the major functions that are heavily used in Wolfram language when performing numerical computing. Now, why a hybrid symbolic numerical method is useful? I'm going to explain this by comparing the way traditional numerical system view numeric problem with the way how Wolfram language views the same problem. By traditional numerical systems, I mean any system with the usual firm separation between the code that's written by the user on one hand and runtime data or variable on the other hand. So this will include things like spreadsheets, numeric metric systems, and programming languages like C and Fortran. So let's take an example to illustrate further. So you want to numerically integrate a function such as this one. So it is integral value from 0 to 3 of ceiling of x times Bessel J1 of 30x squared. Here is the fundamental limitation of all traditional numerical systems. To tell a traditional numerical system to do this type of integral, you first need to write a subroutine to evaluate the integrand. Then you would pass the name or pointer of that subroutine to a numeric integration algorithm in the traditional numerical system. But that algorithm knows only the name of your function and it has no idea what code is inside. From the point of view of the traditional numerical system, the function is basically a mysterious black box. And the only thing it can do with the black box is part in values of x and get out the resulting function value. And by doing that, it will try to build up a picture of the numerical problem. In this way, the problem is that this blind numerical sampling often misses all of the interesting or important features of the problem. You can see that for this integrand, blindly sampling the function hardly gives you any useful information at all about the overall shape or behavior of this function or its integral. On the other hand, now let's compare this with how Wolfram language views the same numerical integration problem. So when you tell Wolfram language to numerically integrate function like this, the full structure of the integrand as a symbolic expression is available to Wolfram language. And there is a lot of information in this expression. Wolfram language recognizes the function ceiling of x and hence therefore expect discontinuities at every integer values of x. Wolfram language can deduce that the Bessel J1 of 30x squared satisfied this differential equation. And from linear differential equations like this, it is possible to construct customized integration rules suitable for highly oscillatory functions. By inspecting the argument of the Bessel function, 30 squared x, Mathematica infers that the specialized integration rule only needs to be used under two rapidly oscillating subregions of this problem, and not on the first subregion. And Mathematica compiles simple mathematical operations like these ceilings of x, 30x squared into optimized compiled functions for faster execution. All of the above things happening automatically behind the scenes when you use Wolfram language and integrate function on this problem. And that's the reason why Wolfram language is able to confidently give you the correct answer. So the big advantage Wolfram language has is being able to see the symbolic structure of the problem. Next, I will show examples of how this information is used, beginning with intelligent method selection. I'll talk about converting numerical problems to standard forms, classifying problems and choosing a suitable class of algorithms, and then identifying cases for which more efficient specialized methods can be used. A great example of automatic problem standardization is the function NDSolve for numerically solving differential equations. NDSolve lets you specify the set of differential equations and boundary conditions in a natural mathematical notation. In this case, the differential equation implicitly gives the second derivative y double prime. And because of this square root, there are two distinct branches or solutions to this differential equation. NDSolve takes them both by first solving the implicit equations, converting into these two explicit systems of differential equations. In this standard form, they are passed to a suitable ordinary differential equation integration algorithm to get the result. NDSolve also handles many different types of differential equations automatically instead of requiring the user to learn the different syntax of a collection of specialized functions. So, sorry. In this example, I'm solving a partial differential equation, and it has to be first discretized and then passed to an algorithm for integrating the problem forward from the boundary conditions mentioned over here. Differential equations combined with non-differential equations are automatically solved, rearranged into a standard form, and passed to a suitable differential algebraic equation solver in Wolfram Language. Likewise, for delay differential equations, in which even the initial history function is easily made a part of the set of differential equations and boundary conditions supplied by the user. Differential equations with boundary conditions at several different points look very similar to initial value problems, but they do require specialized methods. However, user of NDSolve doesn't need to know this fact. In this example, because boundary conditions are specified at 3 different points, the standardized version of this problem is passed to a numerical shooting type method. In addition to interpreting and standardizing problems given in mathematically familiar notation, automatic method selection based on symbolic structure also gives every user access to expert quality methods. In numerical integration, highly oscillatory Fourier type integral arise frequently in many applications. Because of this, large number of very specialized integration algorithms have been developed for of Fourier integrals. Only a small number of experts are really familiar with all of these methods. But because Mathematica is able to symbolically recognize the special cases, even non-experts get the full benefits of these highly specialized methods. In a traditional numerical system, you would either need to be an expert in these methods, or more likely, you would need to settle for whatever generic integration algorithm is recommended. This means getting slower and less accurate results, and we can simulate this by manually choosing a general purpose algorithm instead of allowing NIntegrate to detect the specific nature of the integration. Mathematica gives you certain warning about slowness of the math. Mathematica's n-minimize function is a global numerical minimization function, and it is capable of dealing with a wide range of different objective functions and constraints. But sometimes some specific types of global optimization problems already have specialized methods, and indeed Whole fields of study devoted to them, such as linear optimization with linear constraints, as you see here, which are, of course, also known as linear programming problems. Suppose you are in a situation where the user interactively gives the function all the constraints, or they otherwise are somehow obtained externally from an unpredictable source. You may need to be able to perform a numerical minimization, no matter which function or constraints are given. But if and when a linear objective function with linear constraints is given, you certainly want to use faster and more accurate linear programming methods on that particular problem. And this is exactly what Mathematica is uniquely able to do. Having talked about automatic method selection based on symbolic structure, I will now give you some examples of actual numerical methods that use symbolic computations. So in the examples, I will show two methods or submethods from Mathematica's NIntegrate function. So the first example will be about the handling of a piecewise or a discontinuous function in numerical integration. And the second example is about the construction of customized integration rules for highly oscillatory integrals. So first, let's see why piecewise functions have always been and still a problem for traditional numerical systems. So here is a very simple piecewise function equal to x over 2, where x is less than 3, and equal to 2 over x otherwise. Suppose you want to numerically determine the integral of this function, this shaded area. A traditional numerical method can only do one thing: numerically evaluates the integrand, but getting an accurate estimate of this integral requires accurately knowing the location of the jump discontinuity at x is equal to 3. So an adaptive numerical sampling process needs to repeatedly subdivide and sample closer and closer together in order to accurately model the behavior of this function near this point, where x is equal to 3. In this example, a traditional integration method obtains an error of about 5 by 10 to the power minus 4 after over 200 samplings. And that's a pretty disappointing result of what is in fact a very simple function. Down here, by plotting the location of each sample from top to bottom, you can also notice that the traditional blind numerical method repeatedly subdividing the sampler closer and closer to x is equal to 3 as the algorithm proceeds. So let's see what happens when this same is given to an integrate. The structural dependence condition x less than 3 is detected because we have access to symbolic structure. And NIntegrate uses this information to split the integral at x is equal to 3. Now on the resulting two subregions, the integrand is completely smooth. And in this case, general purpose integration rules are very efficient. The end result is that only 44 sampling points are required to get a result accurate within an error of 3 by 10 to the power minus 14, which is far, far superior to the example we just saw, using a traditional blind numerical method. Similarly, a plot of the location of each sample shows that NIntegrate first took a few samples in each subregion and then made, in this case, just one division on one of the integration regions for obtaining a result with a sufficient level of confidence. Let's take a look at how far this piecewise subdivision can go and how it works. In this integral, the integrand is the sine of a piecewise function. Piecewise function is the min of a linear and a quadratic function of x. Mathematica knows how to resolve the min into subregions on which either the first or second argument is the minimum. After this decomposition, integrand is left with these three subregions. And on each of these subregions, the integrand is simplified into one of the two cases of the min, and on each subregion, the integrand is completely smooth, and general purpose integration rules can therefore operate very efficiently. Piecewise subdivision applies equally well in multidimensional cases as well. In this two-dimensional integral, we use the Boole function to obtain an integrand that is equal to 1 plus cos 4xy on regions satisfying this predicate and 0 anywhere else. The region corresponds to a slice through an elliptical annulus, and the integral computed by NIntegrate is about 1.497, which is the volume of the shaded area beneath this plot of the integrand. This integrand is discontinuous at every point on the boundary of the region satisfying the predicate. Using a cylindrical decomposition and other symbolic methods, Mathematica is able to break up the predicate into these 6 distinct regions on which the integrand is non-zero. In each region, x is restricted to a specific numerical range and y is restricted to a range that depends on the x. Here's a visualization of the 6 subregions Mathematica uses to compute this integral. In this form, a multi-dimensional integration rule can be applied. Although we will see later in the presentation that there is a further symbolic optimization that NIntegrate performs on each of these 6 subregions. So the second example I will show in this section also concerns a class of integrals that have always been difficult or impossible for traditional numerical integration methods, namely highly oscillatory integrals. So highly oscillatory integrals arise often in applications, and they are important enough that in one well-known collection of numerical challenge problems, the first problem was this numerical integral. This is a plot of the integrand. Note that it isolates on infinite number of times in the interval from 0 to 1. Although when this challenge was posed, this was a difficult problem requiring individual analysis, this integral now falls under a broad class of oscillatory integrals that are automatically solved by an NIntegrate function, as you see here. For these type of integrals, NIntegrate uses what is called a Levin-type integration method. So these methods work by approximating the integrals using a more suitable set of basis functions than traditional general-purpose integration methods. So in all general-purpose integration methods such as Newton, Gaussian, or Clenshaw-Curtis, the integrand is essentially approximated as a polynomial. That is, it's approximated as the sum of the basis functions like x, x squared, or x cubed, as shown here. In Levin-type integration method, a different and better suited served basis function is used. The Levin basis functions are basically derivable from a linear differential equation satisfied by the oscillatory part of the integrand, if that differential equation exists and can be found. For this numerical integration, NIntegrate symbolically determines that the oscillatory part of the integrand satisfies this system of linear differential equations of order 2 and then plot. I've showed a few of the basis functions that are used by an NIntegrate function when computing this numerical integral using Levin-type integration method. You can see that unlike the monomial basis functions of general-purpose integration rule, these basis functions bear a strong resemblance to the shape of our integrand, and in fact, they make the integration very efficient. I'm not going in detail about how 11 type methods work in this presentation, but please do take a look at the documentation center of NIntegrate function if you'd like to learn more about that. So here's another example of an integrand for which we can construct a customized 11 type integration rule. And here is the 14th order linear differential system written here in metric form that Mathematica drives and uses for this integral. Now, in the previous example, it's conceivable that you might separately drive the second order linear differential equation and then manually code up a 11 type integration rule for that specific integrand. But it's completely impractical to try to do that every time a different oscillatory integration comes up, especially in symbolically difficult cases like this one. And so for 11 type methods to be useful as a general tool, you need a system in which both the difficult symbolic derivations and the heavy number crunching can both be done automatically for the user. It is interesting to take a quick look now under the hood at an intermediate stage of Mathematica's processing of an oscillatory numerical integration. So using the integral function 11 integrate reduce, we find out that for this integrand log of x plus Fresnel's of square root x over x, NIntegrate has identified a oscillatory function. And there's an additive term, there is a multiplicative term, and there is an oscillatory function, and then the third order differential equation represented in metric forms. For more complete description on 11 integrate data structure, I said earlier, please see the advanced documentation tutorials for NIntegrate. So differential root reduce is an important piece of symbolic machinery likely used by Mathematica in the hybrid symbolic numeric method I've just described. So differential root reduce is used to obtain specific functions like Fresnel S in differential root, from which is essentially our representation as a linear differential equation with boundary conditions. Similarly, differential root reduce is very important in making possible the development of journal 11 type integration rules in Wolfram language. Each new development in the language symbolic engine opens up new possibilities for intelligent method selection and for hybrid methods in Mathematica's numeric functions. So the examples I just showed involves few out of those several unique numerical methods and preprocessing stages in Mathematica. There are many more examples in NIntegrate and other numerical functions, and many more again throughout the wider system, including advanced solvers in areas like probability and statistics, control systems, and many other areas. So in the upcoming section, I'm going to show a couple of ways in which symbolic computation enables automatic optimization. So you may well be amazed to learn how often Mathematica automatically compiles your input without you ever needing to know about it. So when you use a function like table or map to construct list, or in just about any numerical function, Wolfram language compiles your input function if possible, and if it makes sense given the size of the problem. So here in this NDSolve example, after standardizing the problem, including solving the equations for y prime of t as function of y and t, Wolfram language effectively compiles the function like this. The compiled function contains fast, low-level instructions and evaluates many times faster than regular Wolfram language code. The advantage of compiler is also that it performs optimizations, as you can see here. The expression y squared minus cos y x squared contains the sub-expression y squared in two different places. Wolfram language detects this fact and introduces a temporary variable, So you see there's a temporary variable like compile channel $27 to ensure that y squared is only computed once. In this example, the gain may be fairly small, but common sub-expressions like this come up surprisingly often in real situation. For example, take a look at this Bayesian tensor of this vector field. There are repeated sub-expressions all over the place, and when Wolfram Language compiles the tensor equation, it's able to greatly reduce the total number of low-level operations that take place, and this is the resulting compile function. There are many temporary variables defined. And you wouldn't want to have to perform this kind of optimization manually, because Wolfram Language is able to do it for you, because it has access to the symbolic structure of your input function. Sure. Many numerical algorithms, especially in the area of optimization and root finding, perform much better if they have access to the derivatives of the functions being solved or optimized. This is because in case of minimization, the algorithms essentially need to roll downhill towards the local minima. And the derivative tells you which way is the downhill. In this particular example, Mathematica applies a quasi-neutral method that take advantage of the gradient of the objective function. The gradient is easily and automatically computed from the symbolic structure of the input using the Mathematica function d. This diagram shows the steps of the minimization algorithm over a vector plot of the gradient field of the objective function. Here's another example where root finding algorithms use the Jacobian to move forward towards the location of the nearby root. Here's a four-dimensional root finding problem. Now, in a traditional numerical system, for efficiency, you may be well advised to manually compute this Jacobian matrix and then code a subroutine by hand that creates and returns the matrix for any value of arguments x, y, z, and u. Then you would pass that function or a function pointer along with your original objective function into the root finding algorithm. That's the theory. But in practice, most of the time, the user isn't going to bother going to those lengths, especially where they are in the early stages of developing or exploring new ideas. And this means that in practice, gradient information is usually not available in a traditional numerical system. And you'll find that these systems normally rely by default on less powerful generic methods that don't require any information about the derivatives of the input function. Or they may obtain the derivatives by finite difference sampling, which enables the use of derivative-based methods. But again, it's slower and less accurate than having direct access to the exact symbolic form of the derivative. In Mathematica, the derivatives are computed automatically behind the scenes, and they are compiled, of course, as an added bonus. Let's take one more example of an optimization that relies on symbolic computation. Consider the piecewise subdivision example we saw earlier. In this example, the integration region was subdivided to 6 pieces, and let's look at one of the integration subregions, this one highlighted in green. So if integration region is square or rectangular, Mathematica can use pre-computed coefficients and weights to estimate the integral and saves time. Therefore, it would be convenient if we could transform our existing integrand and integration range into a new integrand with integration range that is a unit square. This is done using change of variable as usual in calculus. You may recall that change of variable involves multiplying by the derivative of a Jacobian of the variable transformation. But of course, Mathematica has that part covered. And in the end, for this particular subregion, it turns out that this is the final integrand that Mathematica obtains for a numerical integration. So the original integrand was cos of 5x plus y. So it's different integrand on a different integration region, but the value of the integral is the same. The price of the change of variable is, of course, that this integrand is quite a bit more complicated, but this is not as big a problem as it may seem, because this expression is compiled automatically by Mathematica. And as you can see, there are many repeated expressions and sub-expressions throughout this expression. Just look at how many times expression like square root 3 or square root 3 minus 2 appears and reappear. Mathematica transparently applies this scaling method to all 6 of the integration subregions without the user needing to know anything about it. So each of Mathematica numerical functions also knows about many different algorithms. So normally a suitable algorithm is chosen automatically based on the structure of the input. If you want to specify a particular method, you do so with method option. In this example, we do apply adaptive Monte Carlo method, and the solution is almost a pi. In this example, we compare 2 different methods for solving a large sparse array of equations. So here we created an array of 100,000 by 100,000, and here is the matrix plot of it. And then I use 2 different methods to solve the same sparse array. And using the timing function, we find that for this example, the iterative method is almost like 3 times faster. So you can let Mathematica use its own method based on your symbolic input, or if you want to give your own specific method, you can also specify that. In this example, I choose a specific method called stiffness switching. So the basic idea behind the stiffness switching method is to provide an automatic means of switching between a non-stiff and a stiff solver. So the stiffness switching method traps any failure code which is generated by stiffness test and switch it to an alternative solver. Similarly, the stiffness switching method also uses the method specified in the non-stiff test option to switch back from a stiff to a non-stiff method. Just as Mathematica functions have options, most methods in Mathematica numeric functions also have options of their own. They are specified in a list where method name is first and the remaining elements of the list are its options. So one important special type of method option is a submethod option. So in this example, what I'm using is an NIntegrate function. And the method used is called local adaptive, which is the higher level control method, and the sub method applied to the region also. Similarly, in the below nminimize example, we used a method option to tell nminimize function to start with 250 points in a random search for a global minimum of this difficult function. It is very useful for debugging purposes to be able to monitor the numerical evaluations and steps taken by methods. One fast way to find out what almost any algorithm is doing is to use the evaluation monitor option. You can set this option to an action that you want to take every time the operand of the numerical function is evaluated. In this case, we are observing the convergence of this method to the root of the equation. If you want to get a list of the points sampled or visited by a numerical method, then sow and reap are good choice. So let's watch and integrate converge on more rapidly varying region of this integrand near x is equal to 0. So at each evaluation, we sow the value of x, and at the end, we reap the result and plot them. You can see the convergence of the adaptive method to the most rapidly varying region of the integrand near x is equal to 0. Whereas EvaluationMonitor catches each numeric evaluation of the operand, StepMonitor, on the other hand, triggers at each step of the underlying method, which is usually less often. So StepMonitor is a good choice for finding a bird's eye view of functions like find minimum and NDSolve that operates in distinct steps. So in this example, you can see the convergence of two-dimensional minimization to the local minimum at x equal 1 and y equals -1. One nice way to use StepMonitor is to monitor and visualize the solution obtained so far to a differential equation or other problem. So in this example, we will create a dynamic plot with the current solution of the differential equation stored in the variable sol. So initially, because variable sol is empty, so the plot is blank. But when NDSolve is used, at each step, we will set sol to the current value of the solution, and the result is a live plot showing the current state of the simulation as it proceeds. Thanks for attending this presentation about the unique advantages symbolic computations brings to Mathematica's numeric functions, and I hope you learned some new techniques and functions available in Wolfram Language for numerical computations. Here are some resources which you can use for further explorations. The